Folks, this is video 8 in the playlist which is devoted to motion design in 3D experience, but the kinematic aspects. There are two such playlists. One of them is motion design for dynamic problems, and the other one is motion design for kinematic one. This one deals with kinematic playlist because we're not interested in forces and things like that. Now, the problem that you see here is a ladder leaning against the wall, and this ladder starts sliding as shown here. I have done this problem in several software. One of them was the CATIA V5 DMU kinematics package, and I've also done it in the playlist which is devoted to mechanical uh, systems design. But but the motion design, which is an uh, amalgamation of mechanical system design and mechanical systems experience, is different. The interface looks different, and the functionalities are different. So I'm recreating those videos for this particular application, motion design. Now, here are the dimensions that I'm going to be using, and the first time you saw this problem, first of all, let me tell you what I want to do here. I want that the top of the ladder to slide down at a constant velocity of 100 or 10 millimeters per second, and we're going to do a simulation over a 10-second interval. The first time you may have seen something like that was in your calculus class, where your math prof gave you the same thing, except that says, okay, under the heading of related rates, we're going to solve this problem. And if you look at it, if you look at the expression Pythagorean's theorem, z squared, the height squared, plus y squared, the horizontal distance squared, equal to L squared. If you differentiate both sides, you're going to be able to find the velocity, and if you, or the velocity of the bottom point in the y direction, and the acceleration of it. So your math prof did this thing as a related rates problem in calculus, and that's probably the first time you saw it. Now, here's what I'm going to do. The only problem is that when you look at the previous playlist for this particular problem, I use at the very bottom, I use the sliding joint, slide curve joint, which is no longer available in motion design. So I'm going to create a point curve joint. So the center of that top circle always slides along that vertical line. So it's a point curve joint. And the one below it, because the slide curve joint is available, there's some alternative which is called curve tangency joint. And that's what I'm going to be using. So curve tangency, you have to select the two edges, the horizontal edge of the wall and the circular edge of the ladder at the bottom, and then you're going to use uh, sliding, okay? And if if you may have to flip the radio buttons here so it looks correct. And if the joint is not created for you, any joint that's not created, you can click on the joint icon and create them manually. So the video for doing this problem in the CATIA V5 is actually on YouTube. You can check it out. And please note that there are many ways of doing these problems. Uh, this is not necessarily the only way, the best way, or the most efficient way of doing it. For example, you might say, well, can I do a slide curve joint on the top, on the vertical wall and on the horizontal? Yes, things can be done in other ways, but I'm going to use a point curve joint for the motion of the top of the circle, the top circle, the center of the top circle, and the slide curve for the bottom. Okay, let's go ahead and do that. All right, we are in 3D experience. Let me start with an assembly design. I'm going to do the wall first. Insert a 3D part. I'm going to call this thing a wall. Wall here and wall there. Okay, let's go make it. All right, on that vertical plane, I will sketch my L, which is going to be eventually the wall. So it's going to be this thing here. Because we're doing a kinematic problem, these dimensions don't matter, and but I'll try to stick to what I've got. Okay, so I just want to make sure that this height is 100 millimeter. Okay, that's fine. So exit and then pad it. Default amount, it doesn't matter. Now on that vertical face, I will draw that line, which is 10 millimeters away from that edge. And the reason I do this is because I want to create a point curve joint. So I need a curve here, which right there. And is this vertical? It is vertical, so dimension it to be 100 millimeter. All right. And then make it 10 millimeter away from that left wall. So the distance from here to here is going to be 10 millimeter. And the reason I want this is because notice that the center of this circle, which is radius 10 millimeter, is always going to stay on that line. So that's how I'm going to get the point curve joint. Good, exit. So that's all we want for the wall. These planes are not important, so I'm going to take them away, hide them, okay? It's not important either. Good, so basically we have this gray thingy and a line that is drawn 10 millimeters away from that edge. Now we're going to insert our ladder. So right click, insert 3D part. I'm going to call this thing ladder. Ladder and ladder. And just so that it looks prettier, I'm going to change the colors here. So this is the ladder. I'm going to make it, I don't know, that color. Oops, which I'm going to make the wall. I'm going to make, I don't know, yellow. Yeah, yellow. Okay, let's go make the ladder. So on that vertical plane again, I will sketch. On that vertical plane, I will sketch. Actually, let me go into part design first. We have to go into part design. On that vertical plane, I'm going to sketch. The ladder, you all use this elongated hole. It's easy to make it. Okay, so let's dimension these things. That is going to be 100 millimeter. And there's a circle there, the two ends. I want this radius to be 10. Okay, exit. All right, very good. Now, pad this thing. Oh, it's some same default amount. Now, I want to create a point here because later on, this point, the center of that circle is going to stay on that line. So while we are in the ladder, I'm going to go to point, use the circle center. So I select that circle, and there's a point that's created. I also want to create a point down here in the middle of this ladder because later on we're going to plot the trace of this. So another one place trace of that point. So center of gravity of that face. So it creates quickly a point at the centroid of that circle. Now, what we're going to do is first thing we're going to do is to go all the way to the top assembly and make sure we fix the ladder. Fix the, not the ladder, the wall, fix the wall. Okay, it's created, the wall is fixed. And then, let me expand this thing. And then I'm going to bring this ladder down and put it on that face. And how I'm going to do it is as follows. I'll go to, again, to engineering connections. There is this thing here which is user defined, and this is adds contact constraint. So I'm going to select that. I select that face and this face, and then say OK, and then Control U to update. There we are. Then I'm going to select this point, and I can put it on that curve, right? There's two ways of doing it. One is I can put this thing at that location, and the problem is that that's going to become a spherical joint if I do that, if I go that route. So here's what I'm going to do. Once again, engineering connections. This time coincidence, see that? User defined coincidence between this point and that circle. It's create a new one, and then say OK. Good. Okay. Now, if I want to move this thing all the way to the top, one way of doing it is to go and create, for example, another engineering connection, coincidence between this point and that point, a new one, and then say OK, and Control U. And I don't need this spherical. In fact, if it stays there, this is never going to move. So I'm going to delete this. The whole purpose of that was to put it up there. Very good. That's pretty much it. So now we're going to go to motion design and say OK. And let's see exactly what joints were created here. Notice that the point curve joint was created, and that's what we wanted. Now the other one, this is sliding, we have to do it ourselves, and it was not created. So what we can do is we can go down here to mechanism, click on the joint, and select the what I told you was curve tangency, because there is no slide curve. Curve 1, for example, this curve to that edge. And if that doesn't work, click on the opposite. Looks a lot better. And then we say OK. There we are. So we have created our curve tangency here. All right, now let's move this thing out of the way. I don't like this. All right, good. So while we are in the kinematics player right there, I can click on it and see whether it's actually doing what I want to. See that? It is doing what I want. So reset, cancel. All right. Now we have to add a driver, because we know that the velocity of that point is 10 millimeter per second down. Okay, so we go click on the driver and select that point curve joint, and let me see for a second. I'm sorry, that was selected the wrong one. That's why it didn't look right. So driver, I select the point curve joint. Yeah, driver. Okay, good. Point curve joint, driver. I clicked on the driver, select the point curve joint, and then we're going to go to function. Okay, function. Do I want angle? No, I want velocity to be controlled. Velocity to be controlled. And what is the velocity? It was 10 millimeters per second, 0.01 meter per second. And it's a constant. Okay, you can see that. That's what it is. Okay. And then say, okay, let's see whether it runs or not. Here's a preview. Before running it, we can preview it. Does it go down as we want? So let's see. Okay. What I suggest is that, you remember that 10 milliliter per second? There are other ways to fix it, but here's what I'm going to do. I'm going to go to that driver. And go to there. And instead of 10, I put a 10 millimeter per second, I put minus 10 millimeter per second. There are other ways of fixing this thing. So minus 0.01 meter per second. All right, and then say OK. And by the way, what's the duration of the simulation? Let's check that. Double click on it. Oh, I want kinematic first of all. Kinematic, right there. I forgot this, but that's not why it fell. And you go to 10, and then we say OK. And now let's preview it. Yeah, because it was trying to go up. It had reached its limit. It could not go up. That's why it failed. Okay. Uh, so that's fine. Now we're going to run it. Let me exit this thing. And where is the simulate? We do it over we do it like that. Okay, it failed at 90%, no problem. So let me go ahead and make that time a little bit longer, shorter, maybe 9. Yeah, 9 seconds. Because it could be that it hit the ground. Yeah, the ground at 9 seconds. It couldn't go any further. That's okay. So let's check it out first of all. We click on the results, select this, go to results. Here is the animation. Let's make it go back and forth. Let's see when it's working. Where is this? Yeah. When it was 10 seconds, it already hit the ground. At 9 seconds, it couldn't go any further. So this is fine. Now, the only thing is that I didn't ask for the trace. I forgot. So what I have to do is to go back to mechanism, look at this thing, which is gives you swept volume, etc., geometric trace, and select that point that we created in the middle. Remember the centroid, and then you have to run it because otherwise you won't have the trace ready for you. So we go to simulation, run it, close. Notice that the trace is created. And if you want, you can go here, select your step, go to results, and you can animate it. So that point follows this path that you see here. Also, if you want, you can generate different plots, for example, 2D plot. What I'm going to do is I want some information about, for example, the velocity and acceleration of the center point of this bottom, the bottom circle. So let me go to the ladder. Let me go to the ladder and create a point, center of a circle. This is the center of the circle. It creates a point there. All right. Now I'm going to go to uh, back to the scenario. Okay. So create a probe here. Here is a probe right here. This is not called probe. So this bottom point. Okay. And then we say okay. We're going to have to run this thing. Okay. Go to results, 2D plot. See what we got here. We have a probe, this third one. And let's look at the position of it. The position of it is always, for example, the height of it is always going to be 10. You know that. Let's check that. Yeah. And the y is going to increase, of course. You can see that. And if you look at the velocity of it, velocity in the y direction, which one is it? It's, let me get rid of the stuff that I don't want. This is the velocity. Well, this is the position. Let's try to get the velocity. Velocity in the, this is the magnitude actually. Magnitude. And this can be checked against those plots that those graphs that are, those functions that I have here. And if you look at the acceleration of it, magnitude of the acceleration, So that can be checked against formulas of this type. All right, folks, this is it.